I had the pleasure of speaking with some of you as you're arriving. I guess that this is maybe a little early for some of this content, but we'll see as we go. First off, it's an honor and a pleasure to be here in front of everybody today in the home of Erlang and see so many great faces, some new people, and talk about something that I've sort of been obsessing over for a while now, as thinking through some of the problems that we have and working with software development. And so, from the beginning, I would have to start with this quote here. Mark Twain once said, "There's no such thing as a new idea. It is impossible. We simply take a lot of old ideas and we put them into sort of a mental kaleidoscope. We give them a turn and they make new, curious combinations." So taking this, it's a little sad at first if you think about it. I mean, if there's no such thing as a new idea, then where do we find levels to be able to innovate? And in that case, I'm sure all of us have been in these situations where, we're like, oh, I have this great idea, okay? I love computers, I love programming, I really enjoy waffles. How do I make those work together? I got it. I'm gonna make waffles that look like keyboards. And shortly thereafter, a few Google searches later, you're like, oh, rats, somebody else beat me to it. This happens countless times. I mean, throughout my career, I've experienced so many situations where friends or family even, or just myself thinking about different ideas, different concepts, trying to be able to strive for that one time when I can just be like, I'm gonna have an original idea. Or others, and they're like, this is gonna be great. And you're like, here's 3 people that are fighting for companies that are trying to do the same thing. This guy has a patent, that's weird. So this led to this concept that I had when starting my career, this vision that I had of the world, where we sort of live in the middle, in this middle area, and there's this frontier all around us of exploration that we look for. And just on the outside, there's this line that we draw between what's innovative and what's not, and what's the normal. And so it feels like you need to just spend your whole life working towards getting to that edge. Because if you can just get there, you can have an original concept. And so you start this journey, all right? And this journey is usually just covered with this shroud of knowledge. So we've got this landscape that's just, your worldview. And if you imagine the edges of this shroud as being your your mental capacity, it's at this time when you're starting out in any sort of career area, it's quite small, it's manageable, feeling nice. And so as you start your journey, you start to venture outwards, and you'll uncover that shroud a little bit more, and you'll discover new concepts. And for each moment that you discover, it opens the edges up further. And then you realize not only at that point this new thing that you've learned, but all of these other things that you didn't know that you didn't know. And by this point here, from where we started, tightly all the way on the inside, where we had this just easy worldview, we could see the edges. We knew that there were just these high-level concepts that we didn't understand. It was manageable. But out at this area now, we've explored so much, we've pushed the edge of the shroud back, it almost becomes unbearable to be able to realize that through our careers of learning, we almost know more about what we don't know than what we do. And sometimes this feels tough because you're run down. And when am I ever going to get to that edge so that I can finally have this new idea? And in this moment, I sort of looked back and thought about all of those different experiences, all of the times where you get to the point, you walk up to the next station and you fiddle a little bit, and then you produce an item, and then you look at that item and you're like, that is cool. That is so cool. This has to be original. And you look to the guy next to you and you go, right? And he's like, yeah, I've been here for like a month. And you're like, ah. But looking backwards into this system, we can start to understand these routines a little bit more. So if we expand outwards in one of these sections, we can look at what makes up these experiences. And these experiences are just sort of replaying the footsteps of those people that have come before us. And what we do is we take the knowledge and we use some tools, and we take our knowledge that we've learned, and we use these tools to be able to then create the product. And it's going through these exercises. I mean, as developers, we've all done this routine. Learning language is just like this. Doing anything is just like this. And most of the time, when we take those outcomes actually feed back into our knowledge, and that's what grows our mindset. So we're in luck. Those areas are all around us. We no longer have to just strive to be able to push the boundaries to the edge, to see where that line is, to look out on the frontier. You know, there are new ideas. I should say, actually, since there are no such thing, there are new concepts of things that we can produce out on that edge of the frontier. But we don't have to always look there, because we can look at all the systems that we have around us, because those systems have ways of feeding back into each other. Okay, so let's talk about what you've all actually come here to talk about today. And, you know, it's obviously cooking. We all do this. I mean, you have to eat. Some of us aren't as good as others when it comes to cooking, but it is an extension of creativity, and chefs have some of the most fantastic levels of creativity that they get at their fingertips. So with cooking, I do this often. I like to get together with some friends, put together a wonderful meal, and I find inspiration from all these different places around me. I'll look at different things on the internet about how I want to be able to prepare something. And I'll take the best ideas that I think would taste well, and I mash them together. You know, but first, it takes practice to be able to get to a level where you can start to identify what the flavors are in these different areas. So you have to start out small, something easy. Let's make a pizza. Pizza's pretty basic. I mean, aside from the toppings. People can make it pretty complex, but a basic pizza is all we want to make. And in a basic pizza, well, we have to start by making the dough. So the ingredients in this case, we've got some water, a little flour, some salt, and a little yeast to be able to get that going, and then the toppings. But first, starting by making this dough, we take these things for granted already, in that it would be fairly easy for me to be able to whip this up and make a pizza. It may not taste good, because, you know, there's some, you know, extra ingredients that others put in to be able to add flavor. But in the most basic sense, we could produce this with this ingredient list. The difficult part here is when you break it down. Well, what if we had to make all our own ingredients? What would that be like? I mean, I'm interested in making pizza. Now, I'm not interested in purifying water, or milling flour, or mining salt, or culturing yeast. Those are all quite difficult tasks. But the nice part about this is, in this example as well, as humans, we're social organisms. You know, we gather in events like these to be able to talk and share knowledge. And some of us are interested in solving problems that others are not. And so there's somebody else out there that decided that they wanted to be the best at making flour. And that's fine, because now I can use that as a dependency in my ingredient list for making my goal happen, which is to make a delicious pizza. So another example of this, I mean, pizza is one thing, and using these simple ingredients that still require the work, we can build on that. And if it weren't for that structure of people solving different kinds of problems to produce output that I can use in my recipes, we wouldn't have even more fantastic dishes like this bowl of ramen. So in ramen, there's some basics as well. I mean, this seems like a simple idea, soup. It's so humble. But the first thing we have to do with making ramen is make the tare. And then we have the stock. And then we have the noodles. And each one of these ingredients on its own is such a task to be able to make. I mean, I'm not here to actually teach anybody how to cook ramen, but as a small example of which, to break this down further, the tare, step one here, I'm not going to read all of this because we're not actually making ramen today, but you can see the ingredients, the instructions to make this go on. I mean, you have to take chicken and you have to saute it and you have to then add some oil. And so there's like this experience that's involved in this. And you can see that when you move onwards, that they're talking about ways that they've been able to incorporate the flavors back into it, and you use pans to do it, certain kinds of pans, and put it on a stove. Those are the tools. And so throughout the steps of this recipe, we can see several different things. We can see that the time it takes to be able to produce this individual ingredient, that's not even the reason why we came here to begin with, requires a lot of effort and tools and experience. And so therefore, it's interesting to consider the idea that recipes, they not only are just a list of things that go into producing what you want to produce, but they encode wisdom and knowledge and experience. And in addition, they also use tools to be able to do that. So this mechanism of taking the instructions and applying the ingredients and then adding it to the tools and then producing the outcome, which may also feed back into another system or produce a final result, has a striking resemblance to the way that we build our software systems today. So the same way that we build softwares, we're like cooks. And we basically take our instructions, our wisdom, our knowledge, our way to be able to produce these things. We take our ingredients, which may be dependencies or other pieces of code from other projects. We feed them into our tools, and out comes an application. And so this system is sustainable to the point where when we produce larger level systems, those target applications expand outwards. And this produces a structure that in most cases looks like a lot of the structures we have around us. In the case of recipes, recipes produce food. Well, there's a recipe to make flour. And then when producing that recipe, you produce flour. When you produce flour, somebody else can buy it to use it as part of another recipe. And this tree of dependency just seems to be more and more inevitable when we look around us. And it's no wonder we've positioned our software engineering skills around these concepts. Because not only is it recipes and not only is it software, but if you replace these sections in the middle with people, you can see that we have these dependencies as well. And it takes other people to be able to get to places like this, to walk down a sidewalk that somebody poured, to go over a bridge that somebody engineered, or ride on a plane. And so I say to this point now, a part of a taboo portion, in that there's people out there that look at dependency, and they look at it and they say, dependency is bad. And there's people out there that they look at dependency and they say, dependency is good. And I say in this case that they're both kind of right, but it's not about the dependency. Dependency is inevitable. You can't avoid it. If you were to avoid it, I mean, imagine you're in a situation where where we as a society are working together, but you were like, I am not going to be a part of this. Well, to completely distance yourself, if you took the desert island approach, you'd have to build everything yourself, and you might in your lifetime get pretty far. You might have some skill sets that you're like, I can make this hut on the beach. I can live in it for some time. I can make these tools, and those tools are pretty cool. They're awesome because you made them yourself. But when it comes time for something happens and that system dies and you're no longer there, what matter does it have? That whole system has collapsed. In the case of humans, though, our encoded knowledge that we share, especially through open source software development, travels on for a lifetime and allows future generations and coworkers around us to be able to gain that kind of level of experience. So, an interesting thing about this, because since dependency is inevitable, we might as well embrace it. There was this man, Sir Francis Galton. He was a Victorian-era statistician. And like most mathematicians and engineers that I know, he was obsessed about things like his job and calculating numbers. To the point where, I mean, we've all been there. You walk to a fair and you're like obsessed with how things are engineered or how the rides work. So Sir Francis Galton, he attended a fair in the early 1900s. And at this fair, there was a game. We've all seen this game. You had to guess the weight of an ox, typically count the beans in a jar, something like that. In this case, they had to guess the weight of an ox. And there were over 500 entries in guessing the weight of this ox. And so, as Sir Francis Galton was obsessive over mathematics, he wanted access to those numbers. And at the end of the day, he gained access to all of the different guesses. The contest was over. And what he found was that any one individual guess that was placed in the attendance, nobody was close. They were miles away. And when he took the mean of all the guesses, it was within 0.8% of the actual weight of the ox. This is incredible. And this actually is the reason why Sir Francis Galton went on to produce work in the area of statistics. He's sort of the father of the standard deviation, which, as you can see, would lead to that kind of thought process, that outcome. And through this study, there was additional papers and books that came out. This book here, it's called The Wisdom in Crowds, kind of starts to explore the concepts. Well, if dependency is inevitable, we might as well embrace it. And if these statistics are accurate, then the diversity that we carry in large groups around us can produce some pretty striking outcomes when it comes to steering the ship in the right direction. And it's fascinating to think this way because there are people that you will meet on a day-to-day basis that you might look at this person and you will not get along with their point of view, and you can walk away from that person. And there's other people that you might meet and you're like, I get this guy. Let's hang out together. But you shouldn't write off the other one because in a crowd, you're probably more powerful than actually just pairing up with people that share your same point of view. So with this, I just have to tangent slightly because talking about food, talking about cooking, talking about Sir Francis Galton, while researching some of the backstory for Sir Francis Galton, I found this article here. It's from the scientific publication Nature in 1906, and it reads, "Cutting a round cake on scientific principles." He was so obsessed with mathematics and statistics that he decided that when tea cakes were cut, cutting a slice out of the tea cake as a wedge was the most improper way of being able to keep it from going stale. And instead, you should take a section out of the middle so you can put the pieces back together and you're left with no open surface area that it would go stale with. And then take another section out of the middle so that you can put that back together and make it so that there is no area to be stale with. And you can make a tea cake last 3 days for this part. One of my favorite lines in this actually is where he goes on to have some wit. You know, papers weren't so dry in this case. He had a little wit into saying that the problem to be solved was that given a round tea cake of some 5 inches across, oh, and 2 persons of moderate appetite. So, If dependency is around us and we see this in ourselves, and the wisdom of crowds is going to give us power in numbers, then applying these principles to open source software only means that when we step backwards and we replace these connections with applications, then embracing dependency gives us the capability of steering a ship in a more appropriate direction. And it's at this point where this might be, oh, we're already sort of doing this. And to that I say yes, in ways. For the most part, software with dependency has been the driving force in business, in that it gives us the ability to quickly bootstrap ideas to solve the problems we're interested in solving. If we want to be able to put a camera on something and do computer vision, we don't need to first solve computer vision first. We can just embrace it, and we can do the things that we want to do. This is most of the reason why a lot of the web has exploded in growth. Lots of technology available in software exploding in growth. But this problem is existing elsewhere, in that where I'm specifically interested in tackling is the problem with producing software for hardware. And it's becoming more important than ever that we have an appropriate answer for this case. Because we're starting to see that from the software perspective, the people that are writing these applications are now given the tools and the power to reach down with an open connection to any device that they want to and perform whatever actions they want to as well. But that device that they're looking to reach out to doesn't exist yet. We've seen a lot of these new ideas that have come out. Smart water bottles. One of the most ridiculous ones that I've spoken about before, smart eggs. Huh? Yeah. Some of them are useful, some of them not so much. But the problem remains that with hardware development, we have some different pieces to this. And it always seems like hardware development, and when I say hardware development, I don't specifically mean soldering hardware. I'm sort of shortcutting to say that software for hardware, because we have all of these pieces of hardware available. Typically, you see the opposite. In the case of open source software development for the web, we have pairing sessions, we share information with each other, we produce pieces and components of it that we then just give away for free as open source software. But in the case of developing software for hardware, it's usually done in secret, closed quarters, because I don't know what changes about that, but they feel like this product that they have that's tangible is more important or valuable than the product that they have that's making millions of users happy online, and that even those pieces shouldn't be shared. Typically as well, you'll find hardware developers will couple customized hardware for their needs directly. They'll spend many, many times over months and months and months, years developing this perfect little board that has everything that they need and nothing more, and its sole purpose is to be able to do this task. And it's so difficult then to be able to update it when you look around and you go, oh, I forgot that one thing. Also, the isolated development teams, they're really shut off from the world. And most of the time, these problems arrive in reproducibility, because they always want to be able to reproduce these pieces. And so when it comes to this task, this is where a project that I've been working on comes into light, which is the NERVS project. So the NERVS project is, aims at solving the problems in trying to be able to make producing hardware more like how we're used to producing software these days. We see all of these influxes of open source hardware, Raspberry Pis, BeagleBone Black. We have all of these different targets that are out there that you can just purchase for like little bits of money, and you can get up and running, and you can do the things that you're interested in quickly. And so what is NERVS? Well, NERVS is a toolkit that basically takes Linux and boots it directly to the Erlang VM. And so we try to be able to get you up and running as fast as possible so that you can start doing the things that you want to do, build the smart devices that you want. And so here's how it works. You take your instructions, you take your dependencies, and you take Linux, and out the other end comes a package. So bringing it together, Nerves is really good at building recipes and managing dependency in a sane way. I decided to take this angle and approach in describing what Nerves is because there was a time when I was in a conference in Pittsburgh, Pennsylvania, United States. It was, I was there to give a talk about introducing parts of Nerves, and during the speaker's dinner, it was the first time that I had the pleasure of meeting Joe Armstrong. And I was like, ooh, I get to see Joe. I'm going to rush up to him. I can't wait to tell him what we've been working on. It's going to be great. We've been taking Raspberry Pis. We've been putting Linux on it, and then it boots to Erlang. It's great. I'm like, Joe, check this out. Look, amazing work. Erlang is fantastic. We love the VM. We love it so much. We're putting it on hardware. We're putting it on hardware. And Joe looks at me and he says, that's cute. We did that 30 years ago. Oh, he's right. Yes, it was a great answer. I enjoyed that. And that's why the beauty of the system in this case, yes, putting Erlang on hardware was the original intent of Erlang. So what are we doing? Well, we're making it really easy as a toolkit to be able to build the recipe because Erlang makes a great VM for running on hardware. I mean, it makes a great VM to just want to live in. I mean, half the time these days with the state of operating systems, I just want it to be Erlang. I could deal with that. The problem comes in the case, though, when you start to realize that there are some dependencies that Erlang VM, the Beam, has on the outside world. And there are others in the outside world that we might want to embrace and play along with. So that's why we took the approach that we wanted to bring Linux into the mix, because Linux gives us so much for free as far as drivers and hardware support is concerned, that can very quickly get us to the point that we can boot in Erlang. So with Nerves, essentially what happens is you produce this image that you put onto a device, you boot, the Linux kernel boots, and process number one, Erlang. So all of your initialization of your code, all of your initialization of your systems, including bringing up the networking, happens inside the VM. So if we expand this out, we'll look at what makes up these systems a little bit. And in an embedded system, or any system, you need the ability of doing upgrades or fault tolerance. So we divide the Nerves platform that gets produced into several slices. You have a formatted space that has a position for firmware A and B, including bootloader A and B. But in this case, we're just simplifying and saying, firmware slots A and B. And this lets us do things like always have a last known good working state. I mean, we do get these systems in Erlang to be able to allow us to do hot code upgrades. But in our case, we're embracing the world around us as well and packaging it as a container that when you upgrade, you may want to make changes to the Linux kernel, or you may want to include some additional library like DNS mask or hostapd. That's a Linux tool that you want to exist as well. And so what we do is when you write to these positions, you'll say, okay, I want to do an upgrade. It'll stream the new bits to the firmware B. It'll see if it boots, and you can have a way to be able to get yourself out of the brick state because you always have the last known good working state to go back to. In addition, we have some read-write areas. That's what the spots on the bottom mean, read-only and read-write. The reason we mount the system as read-only is because the beauty in this is that all of the magic happens at compile time. And by mounting read-only, we can make more guarantees that the system will be consistent. So if you need to be able to write data, you can shed off some partitions. You can mount them read-write, or you can also mount them read-only and only flip them on read-write when you want to. And from that standpoint, you can run this on a number of different platforms out of the box. This is a list of officially supported platforms that we have. Raspberry Pi 12300W. The 0W is very cool. and see we have the Linkit Smart Duo. That's another board that's the size of about 0. It's really small, built-in Wi-Fi. And it also has a microcontroller on the back of it that's tied directly in, so you can also do some real-time work with that. And the BeagleBone Black, BeagleBone Green, those are really important platforms because those are actual open hardware specification boards that if you then go to production with your device, you can rework the schematics for that board any way you see fit and not have to do any additional work for licensing. And then what's more fun than playing with Legos? The robotics thing is pretty neat. But with Nerves, we're multi-target. So if you start a project and you want to be able to run it on different pieces of hardware, you can actually target that all of these different devices. And we have some more examples later that I'll show you on how certain people that are commercial companies that are out there producing Nerves projects for their products use multi-target in a way to be able to test things out on different Raspberry Pis, stuff like that. Now, you don't have to just use those pieces. This is the brilliant part about it, is since we're built on top of a package called Buildroot, which is what gives us the capability of compiling the embedded Linux portion of this, Buildroot makes it really easy for you to be able to go in, make the tweaks that you want, changes to the recipe, or even styles to it so that you can boot custom hardware. So if your development team requires the capabilities of producing a board that's got X, Y, and Z on it, you can embrace this for that reason as well. And how you customize your recipe is in the case of this, the Linux side of things, you do it through these kconfig menus. So there's an interface that gives you the capability of editing some of these devices. So, well, a lot of talk is great, and you know, hardware is fun. Talking about hardware is not as fun. So let's play with some hardware. Oh, I forgot to mention as well, you can make additional customizations to this by adding and modifying the contents of the root file system. And if you have any C, C++ code, we'll cross-compile it all for you as well. So, dun dun dun. This is a Raspberry Pi 0W right here, as I was talking about. Very cool. Built-in Wi-Fi, Bluetooth. And let's play around with it a little bit. Can everybody see this? Nice and big? Looks pretty big. Bigger? All right, well, you might not see the file list. That's kind of teeny, but I'll call them out as we go. So one thing I'd like to start with here is getting started with Nerves. So I'm going to just go back a directory here, and one way to get started, first there's installation instructions on our site, and I'll have a slide up later to be able to show you how to get it installed. But Nerves is essentially a shim into Mix, and we bootstrap the Mix environment, which is the Elixir-provided build tool, and that gives you the capability of getting multi-target and all of the functionalities. So the nice thing is that, especially speaking to this conference group here, you don't have to use you don't have to use Elixir to be able to program your application. You can actually include anything that Mix can compile, which I believe, well, it certainly includes Erlang, but I believe that also includes LFE as well, and any other language that can be compiled through Mix. So to get started, we can just type an easy command. We can say mix nerves.new, and we'll pass it an application name, like my cool app. All right, and it'll ask to install dependencies, and you know, why go for this far if you're not going to live? Oh, it blew up. Conference Wi-Fi. That doesn't matter. Anyways, you're presented then afterwards with a list of instructions on how to be able to get started. And luckily, I was prepared for this. I already happen to have an application here. So, what you're producing then is this mix file. If you're familiar with Elixir, or this is your first time seeing it, it's fairly easy to follow along with. The important parts are that we decorate a lot of it with this target. And target is something you'll declare on your environment. You'll say, what board are you targeting? And when the project is generated, the other important chunk are all of these systems that get stubbed out as well. So if you just go and say mix nerves new and you don't declare a filter for which system you're specifically targeting, we'll stub out all the officially supported ones and link to those as well. In our case, we're going to be using the Raspberry Pi Zero, mainly because I'm pointing it at a path dependency and not depending on the network. So all we have to do is set our mix environment. So we'll just make sure we're set with our mix target. All right, and now when we fetch our dependencies, we'll get a nice helpful message that's saying, oh, we have our target set for Raspberry Pi Zero, and we're in dev mode, and everything's good to go. So great. Right from here, we instantly have the ability of saying mix firmware, which is a command that we put in. And what we're doing during this time is we're taking your application, we compile it, we make an OTP release out of it, and then we take those Nerves platform images with precompiled Linux, and we marry the two together, and then we shim all the, set all the permissions. We package it up as a firmware bundle, which is a glorified zip directory. And then that firmware bundle can be used to be able to burn it onto an SD card. So I happen to have an SD card reader here. Let's just plug this in. It'll automatically identify any SD cards that you plug in and burn it to it. All right. Pop this in the unit. And let's give her a go. And there we go, booted in. So on this system, we can see right now on the Raspberry Pi Zero, it makes a great development environment for Nerves, mainly because it runs a serial port over the USB gadget that gives us access in one cable to be able to run serial and power connectivity. So now we're booted into Elixir. We can do things like, let's say, we'll ls on /, and we can see that this is clearly a Linux machine. And we can even check out what's in the bin directory. We can see that there's not a lot there to be able to execute. And the reason for this is because Nerves provides you with an opt-in approach. All right? Some might say, like, oh, why don't I just take Debian and throw Elixir onto it, or throw Erlang and just run it into it? Well, there's a lot of baggage that's involved there. Typically with embedded systems, all of the package management, all of the ability to mutate that over time gets in the way and becomes problematic. I've seen this a lot in production cases where you try to be able to lock down Linux or lock down operating systems only to find that, man, people find backdoors, they find ways around things that you never even thought of. They'll change the desktop background and then all of a sudden somehow some other thing is crashing. It's just a problem. And so the opt-in approach with Nerves gives you the capability of producing really small systems that are very easily distributable, that have only the components that you need to operate. To that sense, Debian and full Linux systems, they may weigh upwards of 6 to 7 to 800 megabytes. Sometimes you'll see installation disks on those of gigabytes in size. This bootable image right here is 20 megs. That's Linux, Erlang, the application, additional userland packages. I mean, 20 megs, that can go over the wire. That can go over the air. It makes firmware updates really easy to be able to manage. And so now we're left with a system that has a little bit of stuff to be able to limp along. Let's make it a little better. Because the nice part about this USB gadget mode is that not only does it give me the capability of running serial, but I'm also interested in running, I don't know, let's say a DNS server and Ethernet on it. So over here, let's say I want to be able to make some configurations. And it looks like my screen's running off a little. Let me shrink this up here for everybody in the back. And there we go. All right, so Nerves gives you access to the tools underneath to be able to enhance your recipes, like build root. With build root, we can type make menu config, if you spell it right. And what this will bring up is the kconfig editor that gives us the capabilities of enhancing what userland things or what additions we want to be able to include, automatically cross-compiled into our system. So I'm just going to use the search functionality. I'm going to say I want DNS mask. It says, oh, you mean this first one up here? And I can say 1, yes, that's what I want. It'll take me right to the place in the editor where I want it. I can hit the spacebar and enable it. And if I go to Control-C to break out of it, it'll say, hey, new config, you want to save the changes? Sure, why not? Now we have it in our build environment. Let's, we're going to use a different command, save defconfig. And what this does is it takes the new config that you've created, it packages it up in a way that it only has the list of short list of instructions that you need to execute, and it writes it back to your original configuration location. And so after save defconfig finishes execution, we'll go, okay, now I'm interested in deploying my application again. So I'm just going to say we'll compile the project, say mix compile, and it goes, oh, I noticed that there was changes to the system. So what we do to track this is we basically take a checksum of the checksums, we hash all of the source, and we tie it to the artifact. And then that gives us the capabilities of understanding when the contents of the Linux area is stale. And through that, we can then put together and assemble a new system. So this, as you can see, may take a while, but it just picks up where we left off last. The rest of the entire Linux system was already compiled, and the changes that we made was that all we wanted to do was install DNS mask, and in this case, it also copied Linux over back as well. It finishes its work, creates the target system as an outlying directory. It puts together all of that into a squashfs file system. It compresses it, and then it moves it back. Now, you can see here, I'm using Docker to do this, because to compile Linux, you need Linux. It's kind of a funny instance. So we provide the ability for Mac OS, and I believe in the future we're going to support Windows with this mechanism, so that you can produce these kind of artifacts. Once it's all done, we're back to our prompt, and we can say we can burn our firmware again. So let me just plug this together. Let's actually, we have to mix the firmware. And burn it to our SD card. Plug this guy back in. All right, and we're back to being booted. So now let's take a look at our bin directory. And we'll take a look at our sbin directory. And we should have DNS mask on here now. Yep, returned nothing, it just didn't run. So there you go. You can install additional packages that way around the user land, but you can also explore some different commands as well to be able to enhance the Linux kernel, make modifications. You can also go so far as to apply patches and pretty much do anything that you need to be able to do to get yourself up and running. I love it when demos work. Thank you. Okay, so I'd like to give some credit to some of the makers. There's two avenues I want to explore to finish this out. One avenue is, who is nerves for? Well, there's a big movement, and I'm sure people have heard this phrase getting tossed around a little bit, and calling people that are like hardware hackers, calling them makers. And the maker movement is pretty big. This gentleman right here, his name's Tim Mecklem. He is responsible for doing a lot of the work, porting the nerve system to be able to run Raspberry Pi 0W and zeros. He is very interested in using these devices specifically because he's working on an open source glucose monitoring system, I believe, and also for interfacing with pumps for diabetics. I believe he's going to be posting a lot of his information online, so keep a lookout for that. In addition, there was another project out recently by a maker who took a Raspberry Pi and nerves and did his own DIY quadcopter from scratch. He wrote all of the web interfaces for it that did a ground station. He's able to, using Phoenix and Phoenix channels, stream real-time data and statistics back to a ground station so that he could modify PID control settings. The thing took off and works. The really interesting part as well is that he's also very avid 3D printer, and so he designed a lot of his quadcopter frames and parts and printed them out on his 3D printer. So that's really, I mean, with some basic tools and knowledge that you can get online, building a quadcopter, that's really cool and dangerous. I've been there. Those blades cut. And finally, we also have, this is from Timo. Timo is a brewer, a home brewer, and what he does is he wants to be able to control the fermentation temperature of his beer. So with a simple Raspberry Pi and a temperature control sensor, he's able to build a really quick nerve system that allows him to be able to make better beer, which is a big goal for a lot of people. Here's a thing that I like to talk about a lot too. This is a project that I did way back where I took my motorcycle through a nerve system in it. This is sort of what inspired me to be able to work on these problems. Make an embedded system into the jacket that worked wirelessly with the onboard computer on the motorcycle and synchronize the blinkers, the stop indicators, and uplinked as well. That's the beautiful part. Oh, thank you. I realized during this experience that it was just too difficult to be able to make these things connect to the internet, because I was first starting with just microcontrollers. Everybody was into Arduino at the time, and it was just so hard to be able to get that thing online, let alone make it secure. And so you had to do so much work to get there, and that's what led us to the position of being able to build these systems that ran higher level languages that could interact with, alongside of, or supervise external microcontrollers, because Erlang's really good at that. But Nerves is not only for makers, Nerves is also being used in production. So I work for a company called The Tote, and we're working with Nerves in production to be able to create devices and interfaces for workers in our distribution center to use RFID to interface and and track the workflow of a lot of the garments that go through our sections. So since Nerves is multi-target, we actually create we are embracing different flavors in our recipe that we use to be able to present an image that not only runs on a Raspberry Pi with a 7-inch touchscreen display, but that same image can also target an x86 all-in-one Dell or an HP computer. And that flexibility gives us the capabilities of simplifying our code base to the point now where that target, we just have to change targets, and we can ensure that some of the bugs that we fix in one are affecting all of our different targets as well. And so this is sort of a deconstructed look at, instead of using one of the standard underlying Nerves platform images, the changes that it required for us to make to be able to let our recipe come together. And one of which is that we compile WebKit in. Because we want to be able to render a web browser to use as our user interface. We compile in Qt because we use Qt instead of any window management system to display to display WebKit in a Chromeless fashion. And as I mentioned earlier, the real reason that we were after this is because we've experienced the pain of having curious hands on a computer that you could, go and open up any other different applications or customize the way the on-screen keyboard looks. This really lets us hone in on providing systems that are reliable and means of performing the job function we want them to perform. And in addition to this, we also added in some serial drivers. Other than us, there's a lot of other companies that are out there that use this technology. There's a company called FarmBot. FarmBot is a California-based organization that is CNC farming robot. It's pretty cool. What it does is it's up on tracks on a raised bed. It's got multiple tool heads. It'll pretty much manage the entire thing for you. And they had different requirements as well. They wanted to have serial drivers so that they could take a Raspberry Pi and interface with several Arduinos to be able to do the steppers. They also had a need for computer vision because they mount a camera on it so that they can identify when the plants reach different growth stages, or also when the plants actually have like weeds around them, or if they need to identify visually any sort of other things. But they also have they made modifications to their Nerves platform recipe to include host APD, because it makes it really easy to be able to configure at that point when it generates an access point, when you buy the thing, to link it with your phone and link it with your computer. Here's a little animated GIF on how the FarmBot works with its computer vision. All that they did was, like I said, they weren't interested in solving computer vision. They just wanted to use it. So they just brought in OpenCV and started using it to identify weeds. And then the FarmBot knows with its weeding toolhead how to suppress them back and keep things running nicely. So how do you get started? Well, we have some great documentation up right now on HexDocs. You can access it through our site, or you can go to our GitHub repository. It'll take you there as well. From there, you'll get all the installation instructions. You'll get some getting started help, and then you can also then check out our examples repository. This is a big collection of just how to be able to use some GPIO. You'll typically get up and running with Blinky, which is the hello world of hardware. Nothing is more exciting than seeing a light blink for the first time, trust me. Knowing that you can write code that can control things like physical things around you is like an empowering feeling, even when it's just an LED. Yeah. You'll show others and you'll be like, oh, look at that light, it's blinking. They don't get it. In addition, we also have a great deal of libraries that have been contributed from the community. People who are using it in production or people that are just playing around with it. On our website, you can go there and check out a lot of these extra things for being able to do stuff with integrating with MQTT or using Fermata, which is a flexible control mechanism for Arduinos. You can also use NFC libraries. NeoPixels are really cool. Those were the multicolor LED pixels that I had in the back of that jacket. They're fun to play with. There's an example of that actually in usage on our example code libraries. And if you have any questions or problems with it, we're on the Elixir Slack channels. We have the Nerves channel, quite active on there. You can check us out if you have questions. You can pop in, ask them away. And so I'd also like to thank Latote, because without them, they fund the capabilities of driving Nerves forward. Without them, we wouldn't be where we are today, and it would take us a little bit longer to get there. But I am sold on solving this problem, so we would just get there eventually. But big thanks to Latote for helping us get things up and running in production. And also a big thanks to everyone here and everyone in the community. Because if we think back to the beginning of this, linking together the concepts of how we all got here with how we act as humans, and how we all connect. We are a social organism. And the more knowledge that we share with each other, and the more chances that we have to be able to take code that we work on and open source it, but not just open source it, to add the instructions, to encode the experience and the wisdom that we have, so that it makes it easier for the rest of us to be able to use that as a dependency. It makes those dependencies have stronger effective outcomes on not only our applications, but other people's applications as well. And it's only going to be able to drive us forward to help us all in the long term. And so whether you're producing just software for the web, or software for computers, or software for hardware, it doesn't matter. The important thing is that you understand that the power is in the wisdom of crowds. And that working together in this fashion and sharing this knowledge is only going to help all of us in the long run. Thank you.
Thank you very much, Justin. Now I need to buy even more Raspberry Pis. I only got 4 of them. We have time for questions.
talked a lot about using all these different microcontrollers and Raspberry Pis and Arduino, all that stuff, but you didn't talk very much about using GPIO, SPI, I2C.
Mhm.
Does NERV support basically hardware interfacing? That obviously does in some way because you were able to talk with your jacket or something. But can you tell me more about that?
Sure. Yeah, so there's a library out there for Erlang called Erlang Ale that ESL, Erlang Solutions, I believe, still maintains. There's also one called Elixir Ale, and it's sort of the embedded actor library. And and those libraries are sort of more an agnostic approach to handling hardware interfacing for GPIO. And it has support for protocols as well, like SPI and I2C, to be able to connect with those kinds of devices and sensors. And so when developing systems using NERVs, you have to sort of be mindful of the approach that you want to take, because inside of Erlang, as you know, we have some soft real-time guarantees. And so if you're interfacing with a sensor that's just a general sensor, like a SPI sensor or an I2C sensor, you can probably get away with that by just using Elixir or Erlang Ale. But if you need to be able to take an approach where you have some more time-sensitive interactions, then what you could do in that case is to use a library like, or write a custom protocol that would interface with a connected Arduino over UART, which UART is also something that we provide an exposure for, to be able to connect a connected microcontroller, so that the microcontroller can manage the hard real-time requirements, and that the soft real-time system, that's the NERVs node, can do what it does best and monitor that and make sure that it's always running.
Cool. Any more questions? I see a distinct lack of hands in the air. Well, I guess it was crystal clear then. Okay, ladies and gentlemen, Justin Schneck.